Many of you already know me. I'm Ben Mauser in the IRC. I'm a third-year undergrad physics major taking a comp sci minor. Also plug my blog, bespokeblog.wordpress.com. You may be asking, what the hell am I doing talking about astronomy at a hackerspace meeting? Hackers love finding out new things, and they like knowing the ins and outs of the system, and what greater system could there be than the cosmos itself. Some of the things that we do as astronomers are real technological marvels. There's some really cool hacks involved in astronomy. Hackers in general love aesthetic beauty. A lot of physics in general, not just astronomy, is very beautifully elegant. It's aesthetically beautiful, both the images themselves and the math and science behind them. Most of you people will recognize the logo I have at the bottom of this slide. Almost every major development in computer technology has at least been somewhat connected to Bell Labs. And interestingly enough, the same goes with astronomy. Does anyone recognize the picture on the left? The left has quicksort and the right is the proton-proton chain, basically the power source of every star in the universe. Astronomy is old as fuck. It's the oldest of the sciences by a long shot, simply because all you have to do is look at the sky when it's dark out and you see that there's a very complex system out there. Astronomy began with the Babylonians between 4,000 and 5,000 years ago. Most of it was wrong. So there were no telescopes, no satellites, nothing, just you standing out there looking at the stars night after night. The word planet actually is Greek and it means wanderer. Planets undergo something called retrograde motion because of their combined orbits with ours. So instead of tracing elegant circle arcs across the sky like stars do, planets will kind of jump back and forth as you track them throughout the year. This is a famous painting, Raphael's School at Alexandria. It's got all the major Greek thinkers up until the rise and fall of the Roman Empire. So you've got people who contributed a lot to the history of astronomy. People like Anaximander came up with a lot of useful techniques, but at the same time he thought the universe was a cylinder surrounded by rings of fire. You also had people like Hipparchus who came up with the magnitude system that we use that basically describes how bright a star is 2,300 years ago, and we still use it today. The big leap forward came in the time of Copernicus, Galileo, and Kepler when telescopes first started to be built, because that allowed us to use magnification and it allowed for a number of discoveries. The left picture there is Galileo's sketch of the moon. Prior to the invention of the telescope, the held belief was that all the celestial objects, stars, planets, etc., were perfect geometric objects, perfect spheres or cubes or things like that. Galileo showed that the moon is just a rocky object just like the Earth. What you do when you do astronomy is obvious. You just look at the sky. But when you think about it, you're not looking at a flat picture of the sky or a three-dimensional model of the sky. Basically, all of astronomy is done on the surface of a sphere, the inner surface of a sphere. Altitude and azimuth is basically height from the ground in terms of angle and distance from the North Pole. If you look at that, that's going to be different in an hour, and it's going to be different on different places on the Earth's surface. So that's useless for describing where stars, planets, and other objects are. Say you have your Earth here, axis tilted because of precession. That's another problem. So you got the Earth rotating, you got it going around the sun, and the axis is rotating like this. It's called precession, and you have, as it does that, it wobbles, and that's called nutration. So these coordinate systems have to change from time to time. We're currently using the J2000 system, which is updated from the old B1950 system. Because of the precession, we have to change our coordinates every 50 years. The declination is basically the height from the equator. All of this is in angular units, again, degrees. The right ascension is basically the distance in, again, angle, from what's called the vernal equinox. Day and night are the same amount of time. One of the problems in astronomy that most people will find is the units are freaking ridiculous. There's a lot of really stupid, pointless complexities added to it because the units we still use are really stupid. Take, for example, the sidereal day. You think that the Earth takes 24 hours to rotate? Not true. Earth takes 23 hours less about 4 minutes to rotate. 24 hours is basically a solar day. That's the amount of time it takes from sunrise to sunrise. But because the Earth is moving around the sun as well, it basically catches up on the sun in terms of the rotation. The sidereal day, which is the time it takes to complete one rotation, is less than 24 hours. Another stupid units issue is the actual units of angle we use. So we don't use decimal degrees or radians like any sane person would use. We use two different sets of units for each of the two axes. Declination is in degrees, but the fractional degrees use the minutes and seconds of arc system. So basically you have arc minutes and arc seconds, and an arc minute is a 60th of a degree, and an arc second is a 3600th of a degree. The right ascension is even worse. It uses the hours, minutes, seconds system. So an hour is 15 degrees of angle. A minute is a 60th of an hour, etc. for seconds. That makes math difficult sometimes when you're trying to convert between units or figure out what exactly is going on in terms of size. Nothing I can do about it. I'm not the Pope of astronomy, I'm afraid. Brightness is complicated too. When you talk about the brightness of a star, you can mean a number of different things. You can be talking about the flux, how much light is passing through a unit of solid angle, which is area along a surface. Luminosity is the total emission of a star. So basically, if you built a Dyson sphere around your star to capture all of the light coming out, the sum of all of that would be the luminosity of the star. Those two aren't the only descriptions of brightness. The one that's most commonly used is called magnitude, similar to decibels in terms of loudness, in that it's a logarithmic scale. Like our ears, our eyes are logarithmic. Something that's twice as bright will not look twice as bright. We've been using this for 2,300 years, so imagine using the same operating system for 2,300 years, the bugs you'd get frustrated with. The other stupid thing is it's negative. A -5 magnitude is way bigger than a +5 magnitude. We measure it with respect to a star called Vega. I don't know why. Pick one. I do not know why we've decided to stay with Vega as our reference source. So something like the sun has a -26 magnitude. One of the other issues in astronomy is something called extinction. What you see there in that picture, funny name thing called a Bok globule, a cloud of cold, dark dust that's blocking stuff. And one of the interesting techniques that you can get around is it's actually linearly proportional to the wavelength of the light. This is in optical, this picture. So you can switch to infrared, see right through it. That's probably the first cool hack of astronomy, is playing around with the wavelength you use. You can see a lot of different things. A hack is a clever way of getting around a problem. So what problems do astronomers face? Ignorance. Fact of the matter is we don't know everything. Not only do we not know the facts, we don't even know where to look for the facts in many cases. This is the first of our Bell Labs alumni of astronomy tour tonight. This is Carl Jansky, and he was basically hired by Bell Labs, among other things, to find out why on earth every 23 hours, 56 minutes, and 4.1 seconds, they were getting lots of noise in one of their radio frequencies. So he built that awkward looking thing on the right there, which is actually the first radio telescope. It was just to figure out, where the heck is this noise coming from? What Carl Jansky discovered was the galactic core. That's how long it took every day for the galactic core to get to the top of the horizon and shine down on us, because it's very noisy in the radio spectrum. By trying to debug their radio communication system, Carl Jansky discovered the galactic core and basically created out of whole cloth the entire field of radio astronomy, which is what I do. I owe quite a debt to Carl Jansky and Bell Labs. Robert Wilson and Arno Penzias. That bizarre looking hunk of cheese wedge thing, it's actually a horn antenna. They were doing proper radio astronomy more than a decade later. In all of their measurements, they were getting a lot of noise at a certain frequency in the microwave range, and they tried to get rid of it. They thought it was instrumentation error. They thought it might be their cables. Eventually, they thought it was actually bird shit on the inside of their horn. They found out that the frequency of the noise they found corresponded exactly with a certain prediction. And what they had accidentally discovered was the cosmic microwave background radiation, which is the first proof we have of the Big Bang. The picture you see there wib-wobbling away is the moon. You're looking over a hot tarmac and you see the waves of heat coming off of that. That happens all the time, just at a very small scale. At a high enough resolution, it makes astronomy very difficult. There's a number of hacks that astronomers have come up with to overcome atmospheric extinction, and I really think you guys are gonna like the first one. Lasers, freaking lasers. What you see there is a picture of the W.M. Keck Observatory in Hawaii. It's an incredibly bright sodium laser to create what's called a guide star. That's a guide star laser. So what you do is you shine the laser close to what you're trying to observe, and since it's a laser, it should be a perfect circular dot. Each of those silver cylinders is a linear actuator. What this whole system is called is adaptive optics. So you have a parabolic mirror composed of a number of smaller mirror elements, all connected to a computer, reading in image data from this guide star laser, and many times a second reshaping your mirror to change the optics of it. The one on the left is basically an image taken through the sky without adaptive optics, and the one on the right is the corrections applied by adaptive optics. The other problem with air is something that Lotek discussed earlier in his talk about ham radio, and that's that air isn't transparent to all wavelengths of light. Really transparent in visible, it's really transparent in certain range of radio, but everything else, it's almost completely opaque. How do you get over that? Well, you put your telescopes in space. This is the Spitzer Space Telescope. It's an infrared telescope in space. It's part of NASA's Great Observatories projects. Chandra, which deserves a little bit extra mention because it's really cool. It's an X-ray telescope. How the hell do you make a telescope that will observe X-rays? You can't use glass as a lens because it'll just pass through it cleanly. You can't use a mirror because it'll just get totally absorbed by it. So what do? You use glancing blows. A nest of really glancing mirrors. Instead of reflect the X-rays all the way back, kind of just bounce them off the sides as these get more and more curved. This is really cool because X-rays are really high energy photons. Chandra lets us look at stuff like clouds of gas that weigh as much as small galaxies falling into black holes. Really cool stuff. The other problem that astronomers face is distance. The universe is really ridiculously huge. Stuff that's far away looks really small and looks really dim. This is actually a computer simulation of the Virgo supercluster, which contains our galaxy and pretty much everything even close to nearby. 31 megaparsecs, that's 31 million parsecs. Parsec is about 3 light years. For light to travel from one end of that to the other would take about 100 million years. And that's just a small chunk of the universe that we can look at. The universe is way bigger than 31 megaparsecs. Easiest way to get over that is to build bigger telescopes. That formula there defines the resolution of a telescope. It's proportional to the wavelength, so that means the smaller the wavelength, the better your resolution, and it's inversely proportional to the diameter of your telescope. So the bigger your scope, the smaller the thing you can resolve. Because of a property of light called interferometry, you don't have to build a telescope that fills up the whole 10 meters or 100 meters or 100 kilometers of distance that you want to get your resolution. You can actually put 2 telescopes or 3 telescopes together, hook them up with computers and a little bit of digital signal processing code, rather than having to build a telescope with a dish that's a diameter of 100 kilometers. You can put 2 telescopes 100 kilometers away and get the resolution as if you had a 100 kilometer dish. Some of the best stuff has resolution on the order of making out a nickel on the surface of the moon from here. You can see there they've got a dish in Hawaii and a dish in Central America. That's basically, in effect, having a telescope the size of like a third of the surface of the Earth to collect your data with. You can throw your telescopes into space and it's like having a dish that's 100 times bigger than the Earth. The reason that most of this stuff is done with radio telescopes rather than optical scopes is you have to know the distance and position of the 2 telescopes to within about half a wavelength of each other. Building 2 telescopes on the Earth and making sure you know exactly how close they are to each other to within a few hundred nanometers, really hard. But if you're doing radio wavelengths like 20 meters, that's That's not too difficult. This doesn't exist yet. This is called the Square Kilometre Array, the Large Hadron Collider of astrophysics. It's a 1.5 billion euro project. It's made up of thousands of small antennas, and the sum of all of the antennas' areas will be a square kilometer in total. It's really, really huge in terms of its sensitivity, because that's a lot of light. That's all the light falling on a square kilometer. In addition to being made out of thousands of small, cheap telescopes, each telescope will be connected to a gigabit network with each other and have a compute node on it in a 1,000-machine cluster that's going to be processing the data the entire array will be bringing in. Finally, what can you do as hackers who want to get their hands dirty with this kind of thing? Become a Mechanical Turk. Be the computer for researchers around the world. The Galaxy Zoo project is similar to the Fold It game, where you fold proteins yourself using your pattern-solving brain, except in this case, you're basically identifying galaxy types. It's a game, basically. You scroll through pictures of galaxies, which are beautiful. Galaxies are beautiful objects, and you tell them what type it is, because your eyes and your brain are way better pattern recognizers than any kind of image recognition software that we have right now for doing this kind of stuff. The other thing you can do is become a comet hunter. This image was generated by a guy who doesn't have any telescopes, doesn't do any observation himself. He basically goes through old data that's publicly available and hunts down comets. This guy's discovered 144 comets since 2000, just by looking at publicly available data that no one's really scoured for comets before. You might think that's boring, and it is, but you have the advantage of discovering something, so that's really cool to have your name behind. And it's also really useful because comets are dangerous in some cases. The more warning we have if there is a comet that might collide with Earth, the better. Naming shit is cool. Having stuff named after you is awesome. And you could, in very, very unlikely small chances, save the world. I've left the most obvious things to do as amateur astronomers to the last. You can observe. You can spend $100,000 a year as an amateur astronomer, but most people here don't have that kind of money. On the left there is an amateur radio telescope that a guy built out of basically scrap steel and stuff. On the right there is a $7,000 piece of equipment called an AOL. That's actually an adaptive optics rig. That has a deformable lens on it that goes over top of your camera, sends out a small guide star laser, and it reshapes the lens dynamically on the fly, letting you do adaptive optics imaging as an amateur. And $7,000 is a lot of money, but it's less than 10. And that's, for a lot of this really expensive stuff, that's kind of the entry level, $10,000. If it's less than that, that's the killer price. And this kind of technology wasn't even around 25 years ago. This is really revolutionary stuff, and it's just starting to trickle in to the amateur market. This isn't something that's going to cost $10,000. Telescope in that range might cost $2,000, $3,000, but you can get that kind of resolution of Jupiter, which is really far away, with an amateur telescope. Normally, I would recommend for people who want to get into astronomy but don't want to spend $2,000, don't buy a telescope, buy binoculars, because cheap binoculars in general are quite good compared to cheap telescopes. Cheap telescopes are crap. Cheap telescopes are absolutely terrible in nearly every way you can measure a telescope as being terrible. But that's changed this year. This year is the International Year of Astronomy. IAU, the International Astronomical Union, has started to mass produce this kit called the Galileo Scope. It's an achromic doublet, so it's two lenses actually glued together. Different wavelengths will curve a different amount, so you basically get that prism effect. By having an achromic doublet, it removes that. It actually mounts on photo tripods, so you don't need a fancy telescope tripod. All you need is that, and which you can get anywhere, and you can basically mount it. It's $15 plus shipping. Shipping to Canada is about $12. So you can get a telescope that rivals a couple $100 scopes that you can get on the market for under $30 shipped to your house. This is a good example of what you can do with this telescope. These three pictures at the bottom were all taken with a prototype Galileo scope. It'll be exactly the same as anyone you would order.
How easy is it to hook up to a camera?
It uses a 1¼ inch mount for the eyepiece, which is standard optical telescope mount. Thanks.